We have a sample problem here. A rigid container holds 2 moles of gas at a pressure of 1 atm and a temperature of 30 degrees Celsius. What is the container's volume in liters, and what is the pressure if the temperature is raised to 130 degrees Celsius? All right, so I have a gas. Ideal gas law is always applicable, and we will end up for part B using a gas process relationship. So rigid container would mean any process that is going to happen is going to have a constant volume. The 2 moles of gas is our N, lowercase specifically. We have a pressure of 1 atm, which we can convert to pascals. We have a temperature of 30 degrees Celsius, which would be, when I add 273, 303 Kelvin. Any time we use the ideal gas law or any relation derived from the ideal gas law, our temperature must be in Kelvin. So knowing this, when we look at the ideal gas law, PV equals nRT, well, we have the pressure, we have the temperature, we have N, so we can totally solve for the volume of this container, which is the volume that the gas is taking up. So 2 moles are 8.31 joules per mole Kelvin. Our author rounds that to those 3 sig figs. Our temperature, 303 Kelvin. So these kelvins are going to cancel, the moles are going to cancel. We do want to put in the pascals pressure, the newtons per meter squared, because of the joule. The joule divided by newtons per meter squared is going to give us units of meters cubed. So 2 times the 8.31 times the 303 divided. I'm getting 0.0497. This is in meters cubed. The question is asking for it in liters. Our conversion is that there is 1,000 liters in a cubic meter. So multiplying that by 1,000, we get 49.7 liters. But looking back, we only have 2 sig figs. So we would write this as 50 liters. So that's our answer to part A. Part B, we're asked for the pressure if the temperature is raised to 130 degrees Celsius. So the pressure we have to start with, if we call those P1 and T1, T2, 130 Celsius, we do need to have this in Kelvin. So adding the 273, that's what, 403 Kelvin. So this is our T2. The relationship when we have a constant volume is that pressure over temperature at one moment in time is equal to pressure over temperature at a second moment in time. So P2 is what we're looking for. P1 times T2 over T1 T2 is 403. T1 was 303. So I don't usually write this all the way out. This will be in pascals. We would want to write this either in scientific notation. So 1.3 times 10 to the 5th pascals, or I'm going to divide by the conversion, the 101/300, and I could write it in ATM. The problem doesn't specifically ask for a specific pressure unit, so either one would be fine. And technically, I could have left this pressure in ATM and come out with my answer in ATM. That's valid. I cannot do that with the temperatures, though. The temperatures must be in Kelvin. The conversion being an addition doesn't work the same way. And so the temperature must be in Kelvin when we use any of these relationships.